The process of system exploitation encompasses several elements. First, you have the exploit, which is delivered to a target system that takes advantage of a specific vulnerability. Then, a payload that delivers some new functionality that you insert into the target system once the exploit is successful. And if all goes well, you're inside the system. Let's look at these more closely. First, the attack methods. There are two types, active and passive. In an active method, we are after a very specific target. We have already identified the target's available services and characteristics and found vulnerabilities that we believe can be used. We've found or created specific exploit code that will exercise those vulnerabilities. We create network connections to a vulnerable service on the target system, and then send the exploit code. If it successfully compromises the target service, then we have our payload code executed, providing the access to the target. In the active attack method, we know a lot about our target system. There is no target user involvement. Contrast that with the passive attack method. Here we are targeting specific users or classes of users. For example, we know that there's a vulnerable client, such as a web browser, that our target user or users have. We want to compromise the user's system by directing their client to communicate with our fake server. So, we wait until that client connection is made. Then our fake server will send exploit code to the vulnerable client and attempt to compromise it. If the exploit code is successful, our payload code is then executed. As you can see, in the end, the result is the same. We were able to exercise a weakness with exploit code and gain access using a payload. Let's visualize these two methods. In an active attack scenario, we have three components: the penetration tester, the target system, and the target network service. The target service has a known vulnerability that we intend to exploit. The penetration tester will make a connection to the target service on the target system. Once connected, the tester will send the exploit code and payload to the target. If all goes well, the target system will accept the exploit code and the vulnerability will be exploited. The payload code will be inserted into the system and executed, and the penetration tester will have access to the target system. For passive attacks, we have the penetration tester again, a listener service, and one or more vulnerable network client applications on one or more systems. In this case, though, the penetration tester is creating a network listener service that waits for vulnerable clients to connect. The clients connect to the penetration tester's listening service. The exploit and payload code are then sent as a response to the vulnerable client applications. In this case, the penetration tester is not targeting the individual systems, but the client applications on those systems. You may ask, how do we know that the clients will connect to the listener service? And that's a great question. The most common way is to send a request to connect, if you will, out of band. It may be an email, a message, fake advertising, a hacked website, or anything with a link that will entice a user to click. Phishing is one of the easiest methods to get users to do silly things. Payload actions are some specific activities that your payload code can do once it's been successfully loaded and executed. Sometimes the ability to use a payload may be dependent on the level of access the exploit provides or the available space that the exploit code has once the vulnerability is exploited. One of the more common actions is to start a shell or command interpreter on the target system. This could be a Windows command shell or a Unix shell. This allows you to execute commands within the context of the privileges that the exploit process has. Executing a command is passing one or more specific commands to the target system. The exploit that you use may be limited but allow local commands to be executed, again within the privileged context of the exploited process. While maybe not as gratifying as the immediacy of a shell, this action may get you closer to the shell that you want or the complete ownership of the target. While executing a command can be helpful, you can also get the target system to download a file of your choosing and execute that. Some payloads allow you to specify a URL for the target. Another one uses DNS-TXT queries to download executable code. Starting a shell is certainly helpful. Starting a programming language interpreter can be even more interesting. These allow you to execute code instead, providing a way of automating the post-exploitation phase. Of course, you can always have fun messing with the user. There are specific payloads that can launch applications on the user's desktop, cause the speech system to tell the user the system has been owned, or pop a message window on their screen with a message of your choosing. Meterpreter is a post-exploitation tool included with the Metasploit framework. It's a highly capable tool designed for providing the penetration tester with significant capabilities for control over the system once you've exploited it. We'll talk a lot more about it later and show some of its capabilities. While these payload actions provide a lot of capability, this is only a tip of the proverbial iceberg. The Metasploit framework allows you to build your own payloads as well. Once the payload executes the action we intend, we need some way to interact with the target system. A network connection between the penetration tester's workstation and the target is needed. Here we'll look at those payload connection methods. The simplest approach is for the payload code to create a listening socket on the target machine and for the penetration tester to connect to it. These payloads are often identified with the word bind in the name. Bind is the name of the system call used to create a network socket. The payload code will create the socket and wait for a connection. The Metasploit framework will attempt to make a connection once the exploit and payload code has been sent. If the connection is successful, the penetration tester will have a shell or interpreter waiting for input. Since this type of connection is the most direct, it will only work if there are no security controls to prevent the connection between the penetration tester's workstation and the target system. The most obvious security control that might be a problem would be a firewall. The firewall allows the exploit and payload code through, since the service we are attacking is public. The listening socket on the target is created by the payload code, but none of the connections to that socket will succeed because the firewall policy doesn't allow connections to the newly opened port on the target. There are other security controls like anti-malware software that prevent listening sockets from being configured by specific policy or without approval from the user. To get around these problems, there are reverse payloads. Instead of creating a listening socket, these types of payloads attempt to make a connection back to the penetration tester's workstation. This is the reverse path, and these types of payloads are identified by the word reverse in the name. In this method, the Metasploit framework on the penetration testing workstation creates a listening socket and waits for a connection from the target system. This method can work when there are security controls that prevent the connection from the penetration tester's workstation to the target, but not the reverse path. Some more aggressive firewall policies may prevent arbitrary outbound connections, so there are payloads that can try many common unfiltered ports to make the connection. If your payload options for interaction with a target are limited, there are also payloads that allow you to fire and forget. These methods are blind in the sense that you may not have any indication as to whether it worked. You may pass a payload that simply creates a file on the target system or executes a benign command. There are no connections made to the target, so no shells or interpreters are started. The outcome is unclear because you have to have some access to the target to know whether it worked. So why take this approach? Well, your job may be just to prove that a vulnerability is significant, not to completely own the system. So if you create a file or execute a command on the target and then show that as evidence, you win. Maybe. Let's look at these graphically. In the forward example, we deliver the exploit code and payload to the target system. The payload code binds a network port with a listening service waiting for a connection from the penetration tester's workstation. The Metasploit framework attempts a connection to the open network port. If successful, the penetration tester has access to a shell or interpreter on the target system. Now let's look at the situation where there is a security control in our way. In this case, there's a firewall. Our exploit and payload is sent to the target service. Access to the service is permitted by firewall policy, so our code slips through. The target service is exploited and payload code goes to work. It binds the network port, starts the listening service. Next, our Metasploit framework makes a network connection attempt. However, it's blocked by firewall policy. Notice that everything else worked. Our exploit and payload made it through. Our payload code ran, and the network port is open and ready. Unfortunately, the firewall prevented the second phase. Reverse payloads make network connections in the opposite direction, and in doing so, can slip through firewall policy. This doesn't always work, but let's look at this example. We have the same firewall. The exploit and payload is again delivered to the target service, which is permitted through the firewall. The payload code runs. Only this time, it will make the connection back to the penetration tester's workstation, which has the Metasploit framework waiting for the connection. It passes through the firewall this time because the firewall has a policy that allows all outbound connections. Blind payloads are those that execute, perhaps successfully, but for which there is no immediate output or other indication that the payload was launched and executed as expected. Just as in the previous examples, the exploit code and payload are sent. The payload code executes, only this time we don't know the outcome. This type of payload may be verified out of band and can often be used just to prove that a vulnerability is significant and worthy of mitigation. If you're working on an internal penetration testing team, this approach may be sufficient to demonstrate the vulnerability. You're in, you popped the shell, and there's a blinking cursor cheering for you. Game over, right? Well, not exactly. Here's where you distinguish yourself from those that would break in just to do real damage. We are professionals, so we have two primary things to do. First, we have to determine if the system has some value to the scope of our testing. Second, we need to establish control over the system so that we can use it later in our testing. The penetration testing execution standard has a long list of activities to consider once you're into the target. I'll simplify our goals and actions here. All systems have information. The question is whether that information is valuable to the organization. If it's the organization's intellectual property, that's very high on the scale of value. What might be even more valuable would be customer data. If the organization had a breach of customer data, it could be even more disastrous. Think about the notifications, fines, and lawsuits that would bring. If we find internal operation information, that can be valuable should we need to go further in our testing. Understanding how an organization operates and the key IT systems used is valuable in establishing further access. That information can lead us to the organization's intellectual property and customer data. If the machine doesn't have information, it might be valuable for the access it can provide. It could be that the system is part of the critical infrastructure for the organization. Think switch, router, server, or even a key desktop system. Maybe we have access to a system with an important user. It might be someone from the executive leadership team. Maybe a normal user that has access to intellectual property or customer data. It might even be the IT administrator with keys to the kingdom. Remember that users are often extremely valuable because they can lead you where you want to go and demonstrate significant value in the testing process. Next, we need to hold on to our access should we need it later. We might find that the system we compromise can be useful for accessing other systems and information. Before we start establishing our foothold into the system, we need to remember to document everything we do on the system. I would recommend the use of something as simple as a command in Kali Linux called script, which records the input and output for a terminal session. Documentation is important for two reasons. First, we want to be able to back out any changes we did to the system after testing is complete. We also need to be able to prove that we acted in accordance with the rules established at the beginning of the project. Enabling access to the system helps when we might need to return. We could try to exploit the system again, but that might be noticed. It's better to look like a normal user. So let's create our own user account or administrator account. We might need to turn on services that will facilitate our access. Again, remember, there may be security controls that might prevent this from working, like a firewall. Depending on the project scope, you may also need to capture passwords or password hashes and attempt to crack passwords. Do this only if it's explicitly called for in your agreement, though. As you will see, the flexibility of the Metasploit framework is impressive. It's also overwhelming to most beginners, so we are narrowing our focus in this course. We will use the active attack method. Passive attacks require a lot more planning and setup than we can cover in this course. Forward and reverse payload connection methods are easy to demonstrate. Blind payloads are more challenging, so we aren't going to spend any time on those. We want to show interactive payloads, so we're using payloads that yield shells and interpreter sessions. The stuff we're not covering here could be entire courses on their own. But let's get started with exploits.